Okay, so welcome back. And in the next session, we have two speakers, I think all of you know both of them. So Carolyn Seepersad and Wang. And in this session, they have kindly agreed to give their perspectives as editors-in-chief of two of the leading journals related to engineering design and systems engineering. So Carolyn is the editor-in-chief for Journal of Mechanical Design, and then Jan is the editor-in-chief for Journal of Computing and Information Science and Engineering, JSICE. So Carolyn, thank you.
All right, thank you, Jitesh. So, and thanks for all of you for being here. It's been a wonderful discussion so far. And so Jan and I are from the same university. I'm going to tell a funny story in that we ran into each other on the lawn a few days ago, and Jan was like, "Have you started your slides?" I was like, "Oh yeah, I got this wonderful compilation of all these articles I've looked at from JMD, and it's all in one slide." And he's like, "I haven't started." And so then, we come together this morning, and I was like, "How's it going, Jan?" He's like, "I got 20 slides. I got 5. Oh my gosh!" And so we've been in a very friendly way, I think, motivating each other. So hopefully you'll be the benefit. I still only have 5 slides, but I'd like to think there's some content in there. All right, so again, these are perspectives just from being editor of JMD for the last 2.5 years and having the privilege of serving the community in that way. And so really not my personal research at all, but just kind of what I'm seeing from everything that's coming across my desk at JMD. So an overview in general of some of the areas that I see folks in the Journal of Mechanical Design community working on in AI and machine learning. And so this probably isn't news to many of you, but I thought it might just be helpful to organize it on a slide as to what I see us doing. So we see a lot of work in concept generation, and I think we saw that a lot over lunch just now. So using particularly deep learning types of techniques, CNNs, GANs, VAEs, those sorts of things for conceptual design and synthesis, so sometimes in topology design. We're also seeing them in mechanism design, linkage design, configuration design. So a lot of work on that area. Also graph neural networks for complex systems with interdependence. And a couple of years ago, our Best Paper Award, our Editor's Choice Award in JMD, was a group of researchers from MIT who were looking at using graph neural networks to build trusses and truss topologies and looking at how they could start to learn independencies and kind of reason from that. We're also seeing quite a bit of work in human-AI collaboration in design. Sometimes it's called that explicitly, sometimes it's not. So we've got AI agents sort of as co-pilots. That's my word to kind of summarize what some of the things that I'm seeing. So we're seeing AI agents being trained as co-pilots to be able to walk a designer or a design team through something. Interactive design, where humans are interacting with AI algorithms in interesting ways. Collaborative decision-making that's being modeled or driven by agents and AI. Design for X, where we're starting to see some design for additive manufacturing, for example, that's starting to use some of these techniques as well. Automated design exploration, so we have been doing design automation for 50 years formally as a community. And so now many of the techniques where we might have used a genetic algorithm or some other optimization technique, or we might have called it surrogate modeling or meta modeling 20 years ago, now we're calling it AI or machine learning in some way. We're seeing some application to predictive maintenance and reliability as well. So using these tools, these are challenging problems where, it might run perfectly fine 99.99% of the time, but you have to be able to target that 0.01% of the time when you have an error or defect or a shutdown. Early stage design, so this is something I would say is a bit newer. So we've been seeing some of the other topics for several years now, but increasingly we're starting to see early stage design work, particularly from the DTM community, that's using things like large language models and things like that to start to mine customer needs and requirements. So one of the things that I did that I thought might be helpful to you, and I think Fayez had a wonderful idea that was very similar, but in a different way. Fayez looked at all the papers from 1978 onward in JMD, and what I did instead was I just took a 6-month snapshot, and what I did is I looked personally at all of those papers in 6 months of JMD, which is the first half of 2025, so it's really quite recent. And I personally looked through and said what I consider what this author has done to be machine learning or AI. So sometimes they would have that in the title or the keywords, sometimes they would not. But there are certain things, like if they're using Bayesian optimization in a certain way, I consider that to be machine learning, depending on how they're using it. And so here you can see there were 65 full-length research papers during that time, during that 6 months. You can see here how they're divided up into DAC, DTM, DFMLC, mechanisms and robotics, and PT is power transmissions and gearing. And then based on these bars, you can see how many of them touched upon machine learning or AI. And overall, it was 2/3. So 2/3 of the papers that were published in JMD in the first half of 2025 used machine learning or AI in some way. And you can see the biggest user of that was really DAC. Well, DAC is obviously the biggest contributor to the journal, but over 2/3 of the papers in the DAC area now. And then quite a few in some other areas. We don't have enough papers, I would say, to really call this a statistical sample for some of the other areas. But you can see that even in DTM, half the papers, machine learning and AI. And you might ask, well, what are they using? What are they doing? And so in the first 6 months, this is some of the things that I saw. Generative design in DAC, you see generative design. We've been talking about that a lot. Not just parts, but also sometimes design sequences. So starting to think about what's the sequence of decisions that's leading to interesting designs. Deep learning and Gaussian processes for prediction. So we've been, if you really think about Gaussian process regression, we've actually been doing that for 25 years in DAC. We didn't call it machine learning until a few years ago, but we are becoming more and more sophisticated in how we're using it. Graph neural networks, large language models for text to CAD. I think you heard Fairness talk about that a little bit earlier. Human AI collaboration, we're seeing that as well. In DTM, some of the things in the first 6 months of 2025, large language models for human-centered design. So even being able to, we're starting to do things like semantic analysis, being able to detect empathy in design, generative design for styling and aesthetics, LDA, latent Dirichlet analysis for pattern finding, multimodal data fusion. And so that's something that I found to be surprisingly prevalent in the first 6 months of 2025. Multimodal data fusion can take the form of some of the things like Fairness and Fayez we're talking about, but increasingly we're seeing it in this case trying to find ways to combine data from different sources, where one source might be a simplified model that allows you to generate lots of data, but it's not as accurate, and then another model that has very accurate or high fidelity data, but it's very expensive. And as we all know, it takes a lot of data to train these models, and so this data fusion then becomes a challenge that's inherent in trying to use a lower cost model to be able to generate lots of data that we can use. So computational agents learning from humans, another thing that we're seeing in the literature as well. And then finally, in DFMLC, not enough papers there to really make a broad conclusion about that, but we are starting to see machine learning for feature extraction, for manufacturability, for predicting properties, especially for additively manufactured components. And in mechanisms and robotics, I think they've been a little bit slower to adopt some of these techniques, at least in the papers that are in JMD, because they're often a little more focused on what's this unique behavior that we can get out of this mechanism as opposed to exactly how we're designing it. But we're starting to see quite a bit there as well. So challenges that I see, some open things that I see that have often been posed by authors. The first that I see is what I call the genetic algorithm effect. And so you have no idea what that is until I explain it to you. So I thought I'd try to gather your attention with that one. So when I was in graduate school, I remember genetic algorithms were quite popular. And it seemed at the time that if you wanted to get a paper published in optimization, you had to use a genetic algorithm. And I'm exaggerating by a lot. But the prevailing opinion at the time was, gosh, why is everybody using a genetic algorithm? And I remember us reviewing papers and rejecting a bunch of them because people were using genetic algorithms just because it seemed sexy and that would get their paper published. But in reality, we all know that genetic algorithms are only appropriate for certain classes of problems, right? If you can use a gradient-based optimization algorithm for something, you should really use it because it'll be faster and more efficient, but people were using genetic algorithms for everything. And so I worry sometimes when I see all these papers coming across, and there are some that come across my desk that never get sent out for review, where people are almost kind of using a Lego approach to AI and machine learning, and they think if they take 6 different methods and they combine them together and they use it to solve this problem, that suddenly that'll be a cool paper because they combine these 6 different methods. So really, I think we have to think about where is it appropriate to use these algorithms and where is it not, and justify it appropriately, because I think there's still a lot of work to be done in our community that doesn't involve machine learning and AI. I hope you guys don't run me out of the door for saying that. Design fixation and bias amplified by AI and machine learning. And so, in additive manufacturing, which I do a lot of work on, it's really hard to get people to come up with new designs that are really appropriate for additive manufacturing, because all the designs that we've seen are ones that we make in conventional ways. We machine them, we mold them, we cast them. And so it's really hard for us as designers to get out of that fixation bias. And I'm worried that these AI machine learning algorithms are going to do the same thing. So we can train them with thousands and thousands of data points of existing designs, and it will give us more existing designs. What happens if we need something that's truly innovative and unique, right? I know, again, that I'm generalizing here, but I think it's something that may be worth thinking about, right? And also, from my background in computational design, I know that interpolating versus extrapolating are 2 different things. And I've always been taught from the very early days of my time in academia by Farouk and Janet to be really careful about extrapolating beyond data that you've trained it on. And so, again, I worry a little bit about that. Replication of results and community building. I think Fayez and a number of folks in the community, when they did a data set special issue back a few months ago, this was also in the first half of 2025 that it came out, they had an editorial that did, I thought, a really nice job of describing the need for archival data sets in design, and a number of different papers that contributed to that effort. But we have challenges there, right, in terms of archival data sets that we can use, archiving them in ways that other people can use them, right, the FAIR standards. Archived algorithms, so we also sometimes have difficulty reusing algorithms, right? If you use a publicly available algorithm that's trained on lots of publicly available data and is continuously changing, it's really hard to replicate your results. And that's very different from, for example, using a Gaussian process regression model that you freeze, upload to GitHub, and anyone can use it. It's always the same when you reuse your data. Synergy between many forms of engineering design data. I think there were some lunchtime talks about representation and other conversations, which is really nice to see. But we've been having this conversation certainly since I was a graduate student and long before that, on the fact that engineering design, you have a CAD model, what was the design intent behind it? How do we record that? And there's so much to engineering design data, so figuring out how to document that in a way that it's useful. We have formats that capture some things well, but we still have this challenge, and we were talking about this earlier today about representation. I think it's still there. The other one that I think I think people are starting to think about, but I'm not super satisfied with the collection of research on it so far, is defining and amplifying the role of the human designer. And so we talk about human AI collaboration, and no doubt we just saw that in the first half of 2025 at JMD. But my question is a little bit deeper, not just how do we get the 2 to work together, but what is it really that we should be preserving for the human designer? So what is the human designer's role in all of this, right? Clearly, I think from the debate that we had this morning, there's a synergy between the 2, but I still have lots of questions in my mind about what is it that we as human beings really bring to this process. Certainly it's synthesis, certainly it's experience, certainly it's empathy with the human condition. Cognitively, what do we bring? And I think that may extend beyond our community into other communities as well. And so I'd love to see more thought on that. And then finally, this is my last bullet, is reimagining design education. And so all of us also teach classes as well as do research. And so I think a lot of us are struggling with what we teach our students today, and how we bring machine learning and AI into that, right? So we're teaching people, we shouldn't be teaching people for the world of 2025, we should be teaching people for the world of 2035 or 2040 or 2045. Because these kids are 20 years old, right? So they're just starting out their career, and it is not going to look like what we're teaching them today. So, even if we give them a class on machine learning and AI, is that enough, right? Because everything we're teaching them in mechanical design is now going to be, a back and forth between AI and machine learning, and how are we bringing that into the classroom. So we do have design education papers in JMD, but I don't really see us yet kind of really crossing over that barrier into taking this research into design education. All right, so with that, I will end, and I'll just advertise and thank all the people who are up here on the slide for introducing a new upcoming special issue on generative AI in engineering design. And so that one's coming up. The call for papers just got released, so keep that in mind as you start implementing all those wonderful ideas that you're generating from our meeting today. And you can use that QR code if you like to learn more about it. So, all right, I will turn the mic over to Jan.
Thank you. Well, it turns out I'm the one over-engineered. But basically, what we're going to have a orthogonal view. I'll say orthogonal view of how we look at the status of the research community. Wait a minute. Yeah, thank you for the organizer for this excellent workshop, and for the opportunity for us to gather and deeper discussion. Right? I think that's very important for a workshop, which usually do not happen during the conferences. Of course, for my presentation, pretty much is the one to give a reflection what you have been working on in the past years, as well as something I have seen probably outside our existing, in this room, some other community-related one, to be probably useful for us. So that is my I would say, the perspective. And by now, this is a fairly genetic algorithm type of terminology we're already seeing. So the key question is, what is happening recently? As we know, machine learning, supervised learning, unsupervised learning, reinforced learning itself is a classic way to characterize. And how do we use these approaches to help us to predict and make decisions? And so we do have some survey paper, review paper available within the journal. This is one of the examples published last year. Through the discussion and this morning, and we do see different types of representation is so important. And Fires gave a very good perspective, that the history, how this AI and evolving, AI ML evolving in the overall community, not just because there's two journals here. If you look at the engineers' jobs are not easy. We have to consider so many things, consider detailed design, say geometry, topology. So those are a very important way for us to communicate as our communication tools here. So graph neural network we have seen recently start being used. Probably some of you already seen those, how to learn this graph neural network. You can have spatial domain learning, spectral domain learning, people developing in the computer science domain. How do we use them? Okay, so that is one important aspect for us to contribute intellectual merit-wise. And the second category, we hope GaTech at least to see more of these publications, paper submissions about so-called neural operators, because this is a way to represent physical models and properties. As engineers, we learn our domain knowledge and then characterize as models, physical properties. And so DeepNet, Fourier neural operator, those are a very important way people develop in a scientific computing community and to represent information. Third one we have seen recently in both journals, of course, JMD and GaTech talk about the transformer-related natural language, syntax of symbols. Those could be relatively easily represented. We have seen also recently the trend, at least from GaTech, is how to combine those two together, or three together. Some hybrid approach will be a very interesting way to extend and to come up a way to have a better performance. And this is, Fayaz mentioned this morning, and this is one of his recent survey paper, the multimodal learning. So that's very important to look into how to represent information from engineering design perspective. Okay, so the text, 2D visual, 3D visuals, data in terms of different form, as well as formula and so on. So this is a very important aspect for us to consider. How do we seamlessly integrate our engineering knowledge into this machine learning tools together? Another aspect is how to represent our knowledge. So knowledge graphs, and in old day, people call it semantic networks. And we have seen recent papers looking into pattern search, and GaTech, as a matter of submitted a paper on the Bayesian inference on the knowledge graph. Very interesting work. And people also talk about user-centric concept design, ontology network, design by analogy. So in other words, how to represent knowledge from the global system perspective. So that's one aspect. Digital twin also have seen recently lots of paper submission within GaTech from the process design, product design, health monitoring, and also human-centered design, digital human. Talk about the human digital the human digital twin. So this is something very important aspect of overall system engineering. For engineer analysis, we definitely have seen the tremendously interest from the detailed design. And Buark actually, he published a paper 5 years back, and it's one of the earliest work on how to use the stress field, how to predict stress field using CNN. And there is some other follow-up, research on those aspects. How do you do the super meshing? In other words, if you have low resolution information, how do you come up with a higher resolution information? It's called super meshing. And there's also uncertainty getting involved, Bayesian neural network. Also, the information comes from different costs, meaning a high fidelity data is more precise but more costly than low fidelity data. So how to combine those data together? So not all training data are born equally, simply speaking. Of course, to look into the most important part is how do you make this machine learning to predict fast? So that's a very, very advantage of this. So those are our different aspects from the detailed design perspective. For system engineering, system modeling perspective, we have seen quite a bit work. And this has been, I just listed some of the recent work. Turnout is one of the most active, sometimes active, inactive, reactive again in our community here. In the morning, we'll also talk about machine learning is about the data. Suppose we don't have enough data, that's a major challenge. How do we deal with that? Turnout AI has a solution a long time ago called rule-based approach, right? So recent work, and we have seen combined rule-based approach and a data-driven approach together to reduce the so-called bottleneck of machine learning. And Janet actually published a paper on the multi-agent rule-based approach as well recently. And so that's something we have seen the combination of the rule-based, data-driven approaches could be the way for us to deal with also the lack of data-hungry situation here. As well as some other modeling methods. Graph neural network, of course, is the most natural way to represent, and also some random graph model and so on. We have seen some of the work recently, and we hope to see more. The reason is since probably more than 300 years ago when Isaac Newton developed all this model until now, we have lots of knowledge accumulated. We do not simply discard the physical model and reinvent the wheel. In other words, we need to train it again, right? Just use data, which is probably not that wise. So recent years, people talk about scientific machine learning, which is also physically informed machine learning. Is combined prior knowledge to guide the training process. So this field actually started 30 years back. As a matter of fact, there are three. This is one of the recent review papers as well, published in GaTech. Three categories: a hybrid model, and so it's probably early in early 1990s. People start talking about how to combine physical model and machine learning together. There's a second approach called a physics embedded architecture, how to combine physics model into the hybrid architecture structures. And the third one probably is the people called PIN, which is the kind of more commonly known. So physics informed neural network is using loss, combine physics information to loss. So just a quick overview what a hybrid model There's different approaches. Three major ways, just combine physical model, machine learning together in a parallel, sequential way. And you can do this design architecture, especially like feature engineering. This approach is also very important for us to deal with the lack of data for machine learning. As nowadays people know, and this physics informed approach has some issues. Training is about you combine the physics model into the laws. It's about soft constraint. And during the process, you just combine different objectives together and train. Ideally, make all the laws functions gradually move on to zero. In reality, there's no way, just because of the training. So in this case, the soft constraint situation has some limitations. People develop different approaches to improve the training convergence. So adding additional regularization, adaptive weights, how the different weights, different loss terms combined together, or dealing with the gradient. So those are different approaches. People try to deal with what's called soft constraint, just because by nature, the soft constraint, the situation combined losses is very hard to get all loss term become zero. So that's a very important aspect to look into the physics for machine learning. Hard constraint is approaches recently people can, well, the soft constraint doesn't work well. How to enforce constraints, such as you have initial boundary conditions, how to enforce that, how you have the physical model, how to enforce that the model truly is satisfied, okay? So, so that is another aspect of interesting direction. And finally, talk about physics for machine learning, and Gaussian process started many years back for our community. Physics-informed approach is also a growing trend, how to embed the domain knowledge into our pure data-driven Gaussian process model. Okay, so this is coming to the very exciting period of the so-called generative approaches, and we have seen a lot, and in JSI's, and starting from the early version of the generative advisory network, and we have seen quite a bit of work published. As well as, the key here is the one to show there are some hybrid approaches. Simply speaking, this is kind of growing trend, how to combine information, different modes together. Diffusion models, similarly, how do people combine together? And that's way to fit us, talk about a GenCat, that's one of the interesting aspects to see. How detailed design could be integrated with the latest, so-called a large language model or diffusion model. So there's a challenging issue in terms of representations too. Okay. Okay, I'm going to probably quickly go through the end. That hybrid approach probably is the one people have seen to be useful. And we have different, different special issue published recent years. And one of them is large language model published earlier this year or last year, actually. So we have seen growing interest in using the large language model to do the conceptual design, CAD generation, document design, and people talk about cognitive aspects, sentiment analysis. So in other words, we could utilize those latest tools to do a lot of things, and do a lot of things here. Design education, so which is very, very important for us to move forward to look into this. So the last, this probably is the, okay, so this is physical AI, people already talked about this morning, and just important part of the survey paper the recent published is about to look at the historical vision perspective, have symbolic AI in 50s, and to look into the behavior, expert system. So the AI evolve, and sometimes probably go back, recycle. So the thing is this, our domain knowledge as a physics or physical AI, regardless of your application in robotics or engineering simulation, so considering physical knowledge will be very, very important. Okay, so last one, and just highlight a few challenges or opportunities going continuation of so we talk about the through the discussion throughout the day, we have seen so many challenges: training convergence, representation, and in the morning we talk about the uncertainty, the epistemic uncertainty you have incomplete knowledge. Data imperfection, we have known that, and the one aspect is the physics data conflicts. You collect data, data is not perfect, and sometimes it is contradict with your physics model, and how to deal with that. Okay, so interpretability and how to generalize, how to do the extrapolation. So far, we haven't found a good solution. Hallucination, so the trustworthiness and ethics. Even computer science folks talk about the channel verification and things like this. Probably still at the very early stage. So computational efficiency and high dimensionality, those are very, very important aspects. How to use those tools, develop such tools will be useful for us. I think that's my 20 slides.
Carolyn and Jan. Do we have any questions or thoughts that anybody wants to share? Yeah, sure. Do we have another mic?
Great. Yeah, thank you for the overview. I guess I had a couple questions. So are there any, I mean, when you looked at sort of the AI portfolio across either JSUS or JMD, were there any articles that you were like surprised that were missing? Like you were like, oh, I was kind of expecting more people, like given all that thing, like why didn't somebody do, I don't know, cost estimation or something? Like was there anything that sort of the field's not working on that sort of like is an obvious thing that we should be doing that just like given your sort of broad purview, you were like surprised that you didn't see?
Okay, I can try. Okay, I'll try. Okay, through my crystal ball, Mark. Yeah, I think, so I think a couple of things I mentioned there, right? I mean, I think there's an opportunity for more work on AI and sort of design education. I mean, we do a lot of work, especially in sort of the DTM area on, using students as our subjects and thinking about how when we introduce a tool or a different tool, how does it affect the outcome of a student team's design project. But I think I'm thinking more than that as to how do we kind of use AI machine learning in the classroom to accelerate or facilitate design. And I'm not seeing that yet out of our community. And so that to me seems like a really big opportunity. I think there are some opportunities in overlap. So I think in the community, when looking back at JMD, maybe when I first became editor in 2023 and before that, we were using AI machine learning an awful lot in what I would call design automation applications. I mean, even if it was published in DTM or said it was a DTM application, it was really kind of, in many cases, in most cases, in almost all cases, a design automation, more of a process. It was about search, exploration, optimization, other things like that. So I think we're seeing more and more application to DTM, but I think there's also opportunities to do more multidisciplinary crossover, right? To start to think about, well, how can we use AI machine learning to do, both search and say sustainability, or both search and manufacturability, or other things like that that kind of extend our purview of what we consider to be our core, design problems. So I think there's a lot of opportunity there. And I think that may be something that will happen naturally, right, as we evolve, because, tools and techniques kind of start in a core area and then they start to move out. So I think we're already seeing that.
Yeah, to add that one on, to me, surprise is engineer analysis, physics-based approach for detailed design. I wish I have seen more paper submission on this site, because Barack have a very good comment this morning. How detailed design could be simply replaced by AI model, so that the human can be have more time to think about some other things. I have a little different perspective is based on what we have seen here. Even so, we still cannot trust AI or machine learning model to design airplane so that I feel safe to fly with. So I think in this case, I wish more work in the actually go down the detail level. Detail design is very, very important. We have to look into, people talk about in the morning about the verification and validation, those things, very, very important aspect. We still haven't reached that stage that we can truly trust the AI to make something we can fly with, we can drive with, in the human knowledge traditional physics-based simulation-based approach in the design. I think that's what, but I think this could be the great opportunity, and there are new tools. I believe computer scientists probably cannot develop such tools for us, and rather we need to go opposite, to go to the scientific machine learning in general, for instance.
I have a general question about the trends in the field. So right now, if we see this year, big computer science conferences, which were already quite big, have exploded. Like AAAI had about 25, 30,000 submissions, and similarly NeurIPS and all of these conferences. And people are just being crushed by how many papers are being submitted in these computer science conferences. With this explosion, whether it's good or bad, like, what role do you see, like, our community, like, is this explosion affecting JMD JSICE also? And like, is there both ways, positive or negative impact on our field, on our kind of publication venues moving forward?
Yeah, so Fayez, that's a really good question. So I think there are a couple of different effects that I see. So as we converse more and more with some of these other fields, one of the things I'm seeing, and I'm a little bit worried about it actually, is that authors who really take, say, AI machine learning and follow it to its logical conclusion may be starting to put their papers in other journals where they feel like they have a much broader viewership. And so to some extent that I'm being a little bit selfish here about JMD, okay, I'll be honest with you, is that I'm worried that it may hurt the quality of our journals. So kind of trying to come up with special issues like the one on Gen AI that's coming up, and the the data sets and design special issue that you put forward, to make sure that we still stay, that a lot of our best papers still stay in a community where they're going to be seen by people who need to see them. So that's one thing that kind of concerns me a little bit about that. But I think otherwise, coming back to some of the comments that we saw this morning about, I'm not remembering who exactly said it, it might have been you, it might have been someone else, about how we are the community that, it might have been Mark, that we are the community that has some of the most challenging problems for these algorithms. And so I haven't attended one of those broad AI conferences in a while, but I have a few years ago been to some where there have been computer scientists and things like that. And one of the things I find is that the problems they try to solve to us are just completely trivial, or at least some of the problems that they're trying to solve, like in computer graphics and things. We have the problems that are much more challenging. And so we have an opportunity to kind of bring them over to our field and say, hey, look at us, right? Work with us. We understand these problems. And they're much more challenging for you to solve than the ones that you might, the benchmark problems you might be trying to address.
To add on that, we have a similar situation compared to JSA compared to JMD. We do have lots and lots of submission and machine learning related, and so people ask, okay, so what's we have JSAS in mechanical engineering, so we keep emphasizing this. JSAS is looking into the fundamental research on the methodology development of machine learning, computational modeling, for instance. Methodology is our emphasis here. So given that there are lots of submission here, and we do just see those papers just simply apply existing approaches to solve the problem, machine learning especially, and then this we'll probably have to tell the author that doesn't fit our JSICE. So this is probably a good part, of course, is we do have a submission which has a good visibility in terms of why we have so-called computational thing with a mechanical engineer. So that's the one. Of course, the downside is we have to screen out a lot of papers. So down the road, I'm also optimistic as this conversation continue. We do understand our expectation will help our authors to learn how to write papers will fit into the JSAS scope better.
Thank you very much. Kind of building upon the point, Jan, that you just brought up, I'm curious to in both of y'all's recent experience, are you seeing papers just take existing algorithms and apply them to engineering problems, or are you seeing something specifically unique about our engineering design problems that's influencing how these algorithms are made going forward? Where do you see the future going there?
Okay, so we have seen the simple application, and turn out a simple application will not a good value in longer term in terms of archive value. What we have seen is the paper were published tend to be more selective in the sense that do we have longer term impact, say 5 years, 10 years from now, people still like to read to feel the value of this intellectual merit. In the future, we think our community here within mechanical engineering does have advantage compared to other mechanical engineering, so-called sub-discipline. We emphasize computational, emphasize methodology. So this could drive back to say, how do we advance machine learning, AI approaches solve engineering domain problem, which do not exist in computer science general discipline. So I think my perspective is optimistic looking to the people here in the room, very smart people here can come up with something revolutionary and in other words, go beyond existing computer science folks are talking about, just be bold.
I guess from my perspective, I think there's room for both. There's room for both algorithm improvement, and then there's lots of room, at least in mechanical design, to use algorithms that are already out there. So I think you see two classes of papers in JMD and the mechanical design community in general, right? There are those who develop new algorithms, and one example that might come to mind is data fusion from multiple sources and finding new ways to do that and to use data more economically because we're forced to, right? We're not searching through these, in many cases, these huge public databases with millions of data points. We might have to run a CFD every time we want a data point. So we're forced to do that, and so we've got these more efficient algorithms that are coming out. So that's one side. But the other side is I still really appreciate opportunities to take algorithms that are already developed and apply them to design, because that's not a simple task in many cases, right? Just this idea of figuring out how to represent a problem so that it is amenable to the use from a machine learning algorithm, right? Thinking about, for example, some of the talks we've seen in being able to represent or recreate CAD models, right? If you use just a general VAE and sort of image base, you get this gray image back and this sort of grayscale image, and that's not useful for actually manufacturing. So thinking about how we represent design so that we can use these algorithms, and at the other end of it, how do we measure the outcomes and what's important to us, right? It may not necessarily be just does it look crisp, but it might be, is it manufacturable? Does it have a fatal flaw that means that it violates a law of physics or what have you? We are kind of in the mechanical design community well positioned to evaluate all those things. So you've got machine learning algorithms kind of sandwiched in between what do we feed into it, what's our representation, and what comes out of it, and how do we evaluate that? And we are uniquely positioned for both of those things, and I think they could be even more challenging, right, than developing the algorithms that go in the middle of the sandwich, if that makes sense. Yeah.
Thank you both. So maybe I want to ask a more practical question since you're both here. So many of us publish across both journals, and I'm curious, what type of heuristics should we use as a community when we're deciding between, JSICE and JMD? Is there anything that you hope that we keep in mind? Especially, I'm seeing a lot of special issues recently that I feel like they could appear in either journal. Quite honestly, like the generative design, it's a really interesting and rich topic. It could go in both, perhaps. So.
Yeah, that's a great question. And I think that, from my perspective at JMD, looking at the papers that have come out recently, I could certainly do a better job of moving some of those over to JSICE. So I think that the way that I personally view it, and Jan can jump in, is that when we're talking about design purely, like we're really talking about coming up with new designs, we're talking about synthesis, and that the contributions are in applications to design, in my mind, that is a JMD paper, right? If it's a paper where you're focusing just on modeling, for example, but you know, clearly that maybe it's surrogate modeling or something like that, that could still, we can see how it would be useful for design, but really your focus is more on, you know, physics-informed neural networks or something like that, but not really quite taking it to the design level yet. In my opinion, I at JMD should be pushing that over to Jan, right? So I think there's definitely a little bit of overlap just because the CIE community and the rest of, say, DETC do have some overlap between them. But that's kind of my view, is if it's clearly there's design synthesis, then that seems to have a more familiar home in JMD. And we've had similar sorts of overlap conflicts before. So JMD, Mechanisms and Robotics, spun out from JMD. And so if you go back a few years, there was only one journal. And when those two split apart, the decision was that anything that's more analysis oriented goes to M&R, Mechanisms and Robotics. But if you're really designing something and you're thinking about how do I design this mechanism, how do I design these linkages or these compliant mechanisms, that really needs to go to JMD. So, you know, thinking about there's precedent in the past. We don't always do a beautiful, perfect job of doing that, but in general, that's the goal. So Jan might have some additional thoughts to share.
Yes, indeed. As both journals evolve, especially this driven by the AI, ML. So we emphasize the methodology, computational algorithm, right? So in other words, if you emphasize design, particularly concepts, methodology, JMD definitely would be a more in a better position to publish. At the same time, of course, there might be some overlap, and there are some methodological, emphasis within JMD. I would say there's some, so there's no clean cut. Is probably towards the end will be our authors' preferences towards the very end. But in general, and design methodology-driven paper will be the JMD side. On the other side, J side doesn't just a design paper. You notice that we emphasize methodology could be design, could be manufacturing, could be a cyber physical system, could be human, could be VR, AR, and could be many other engineering disciplines. So I think design will be a subset of J size in terms of application. So I think that's probably a good way to differentiate.
The other thing I'll mention is because we're both ASME journals, we actually have the ability to move papers across from one journal to another without asking you to resubmit. So if at any point you feel like, I'm not quite sure, you could submit and send one of us a message. We can take a look. And if we think it's better for JSize or JMD, we can behind the scenes just transfer it over and transfer everything along with it. So you don't even have to resubmit. So that's an option as well. So for you guys, you don't have to worry too much about which one you send it to. We can always reassign without any extra work on your part too.